X-rays, and then we are going to move to the Auger electrons. And for the X-rays, we discussed how do we detect X-rays. We detect X-rays with two different kinds of detectors. One which is called the wavelength dispersive detector, and the other one is an energy dispersive detector. And the wavelength dispersive detector, which you see here on the left, is sequential. It does one wavelength after the other. It sets up the diffraction condition for that particular wavelength. It has a crystal, it sets up the diffraction condition, and then it scans over different wavelengths by rotating the diffracting crystal. And as a result, you can see that the peak widths are very narrow. The full width at half maximum is quite small, and you can see that you can resolve finer features in the spectrum. On the other hand, if you look at the energy dispersive, you look at the energy of the photons that come through, and you use a silicon detector or a semiconductor detector. The simplest one is called a SiLi, or a lithium drifted silicon detector, and that detector gives you roughly about 140 eV resolution. So the peaks are quite wide, whereas here it's about 5 eV. So you can see the peaks are much narrower in the wavelength dispersive case. All right, and the other thing that we also saw is that the reason it is like that is because you have to build a crystal that works at low temperature. That means it has to be cooled down, and when it is cooled down, you want to make sure that no water vapor condenses on it. So you put a window in front, and then you put 2 coatings of gold, so you can put a potential across it and pull out the electron hole pairs. So even though the silicon band gap is of the order of 1 eV, it takes about 3.8 eV to create an electron hole pair in this lithium drifted silicon detector. All right. Now there is one other thing that I did not mention in the last class. And what I did not mention in the last class is that this detector, if you look at this detector, this is a typical detector, it has a certain thickness. Now, X-rays get absorbed in materials, and they go, the transmission goes exponentially, drops exponentially with the thickness. So if you look at the intensity, it's going to be I0, which is the incident detected, and then exponential minus mu x, where mu is the linear absorption coefficient. Sometimes it's written as mu over rho. Then it becomes mass absorption coefficient. So in that case, you put the density in there, and therefore whether it's a liquid or in a solid form, it doesn't matter because you take care of that by the density. So then if you change this from mu, if you write mu over rho, and then you multiply by rho, you have essentially the mass absorption coefficient. You take care of the density. Now, if you look at this, you plot this, it's a function that drops exponentially with thickness. So if you have an intensity here, initial intensity here, if you're going through a material of different thickness, as the thickness increases, the intensity keeps dropping down exponentially. Okay? Now, there is, at a certain point, if the thickness is about here, if you have I0 coming in here, the I that will be coming out at this end, so the X-ray will just go through a certain thickness, right? So if you look at this detector now, the detector has a finite thickness. So if the energy of the X-ray is too hard, then what will happen to the X-ray? It will just go through this detector undetected. It will not create any electron hole pairs. So if you look at the efficiency of this detector as a function of energy, it will have very high efficiency beginning, and then it will go down, and then it will go down like that. Right? Because what it is doing is that high energy X-rays are going through the detector without getting detected. So if you want to increase, if you want to be able to detect higher energy X-rays, what would you do? What would you do? So now, let's say the silicon detector has efficiency up to 10 kilo electron volts. And after that, any higher energy, the X-rays will go through without being detected. So now if you want to detect something at 20 kilo electron, like a Moly K alpha, what would you do?
Can you go to a higher density semiconductor?
That's exactly right. So you go to a higher density semiconductor, like a germanium detector. So you go to a germanium detector, then you can go up to somewhat larger energies. Or you have to detect not the K alpha but L alpha lines, which have lower energy. So what I'm showing here in the next slide are essentially the efficiency curves. So the dotted line is for the silicon with drifted with lithium. You can see it's pretty good up to about 20 kilo electron volts. And then the efficiency drops. But if you go down to the germanium detector, it stays quite high efficient up to about 40 kilo electron volts. And then the efficiency drops. Is everybody clear on this point? That because of a finite thickness, the X-rays sometimes will just go through the detector without being detected. Have a question?
I don't entirely understand why just because the semiconductor is too thin, it won't be detected.
So, okay, please ask this question because this is everybody can benefit from such questions, right? So, when you have some sort of photon coming in, it has to hit the atomic core, right? In order to create an electron, to create some sort of electron hole pair, it has to hit the electron. But there is something called a scattering cross section, right? That tells you what is the projected. So you have atoms sitting here, and they are inside. What does it project? What does it show to this X-ray that is coming in, and for it to hit that? So there is only a finite probability that it will hit an atom as it goes through a certain distance, right? Now that finite probability is higher for the higher atomic number element compared to a lower atomic number element.
Okay, that makes sense. Actually.
And so for a given thickness, the higher atomic number element will produce more electron hole pairs compared to a lower atom, because there's no, the photon is not hitting a particular electron to create an electron hole pair.
Okay, so that's just based on the probability that it
Yes, exactly. That depends on the atomic number, yes.
But does an intensity curve drop off faster for a denser element?
Yeah, because it will have this one and then it will rho times mu times here.
Yes, so
Mu of
you
rho.
get lower intensity.
Yeah, exactly. Any other questions? So that is why we build this intrinsic germanium detectors rather. And germanium does not have the same kind of defects that silicon has. So you don't need to compensate for those defects. So you can just use a pure germanium crystal. So if you do experiments for astrophysics experiments, where you're looking at other radiation there, you use a germanium detector. High purity germanium detector is very sensitive. It does not have these intrinsic defects. So it will create immediately the electron hole pairs as soon as some sort of a photon of a certain energy hits the detector.
Sorry, but if you have a very sensitive germanium detector and it has low intensity, wouldn't you have how would you solve the signal to noise problem?
No, in fact, the signal to noise is very good because most of the collisions produce electron hole pairs. They don't produce, they don't just produce random things, they produce electron hole pairs. So the signal is good.
Oh, okay.
That's why you see the efficiency is close to 1 all the way up to this. So you have always producing electron hole pairs all the way up to about 45 kg. And you see the efficiency is very high. There is a small, can anybody explain why the drop off at the low energy is so rapid drop off? Yes? No. I've already explained it from the physical nature. You have this window that absorbs the low energy X-rays because we have to put a window in front. right, to protect it. There are very few of the modern ones which have the windowless detectors, but you always have a window in front. In the old days, it used to be a beryllium window, a thin layer of beryllium in front. Then they put on a polymer window. But the beryllium window is solid, but it absorbs all the low atomic number elements below, let us say, atomic number 10. So that's why that efficiency for the low energy, it drops off. That is, the low energy is the low atomic number elements which are absorbed in the window. So on the one side you have the window, the issues. On the other side, it's just the X-ray just going through undetected. So the efficiency drops at one end because of the window, at the other end it drops because of the X-ray just going through undetected. Okay? That's why you have this efficiency curve. All right. So we have done this. There's one last thing that we discussed at the end of the class last time, and that was this particular slide. And we showed two things here. So the X-rays, in this case it's actually electrons, it's an SEM or a TEM. You have high energy electrons incident on a material, and it produces X-rays that you're going to detect. So this electron, as it is going through the solid, it's also going to scatter and lose energy. And so as it's losing energy, at a certain depth, it will have zero energy. So start with the initial energy, it's going to start losing energy, and if it starts to lose energy, it will have at some point not enough energy to excite a characteristic X-ray line. You have to overcome the binding energy. So it will not have the sufficient energy. So if you look here, as it is losing energy, the dark gray area is that it has enough energy to excite a copper K alpha. Then it loses more energy, and then it has only sufficient energy to excite the aluminum K alpha, which is much lower energy. And then it loses all its energy and it becomes zero. Just then, there's no more energy to propagate in the material. And the same thing is shown on this side. The only difference is the density of this material. The density is 3 grams per cc. This is 10 grams per cc. And since this is more dense, it has less depth that it can propagate. So the initial intensity is now affected by this atomic number of the material that you're trying to analyze. The depth that it can propagate will depend on the atomic number. Right? Now the second thing that I pointed out is that you have a detector at a specific location. That means the X-ray that is produced here has to travel in a straight line to the detector to be detected. And so there is that distance that the X-ray has to travel in the material itself. And in the distance that it travels in the material, we pointed out here that the intensity is going to drop. And therefore, there is going to be some absorption of the X-ray. Right? So there's going to be some absorption of X-rays in the material. And the third thing is, and then it's going to be detected. But X-rays of a higher energy can also be used to excite X-rays of lower energy. So if you have a K line, which is at 20 kilo electron volts energy, it can always excite an L line at say 5 kV. So this process is called fluorescence. So the intensity is also going to be now affected by all these parameters. The atomic number, so that it tells you how much the incident electron is propagating in, the absorption of the outgoing X-rays, and the fluorescence of this. So the intensity that you actually measure is going to be this, and the intensity that is produced. It has to be, this has to be corrected, this has to be corrected for this. So you have to correct this, and this is typically called this ZAF correction. Okay, so we did, the last class we showed that the intensity of the X-rays that you have is proportional to the concentration or the number of the atoms A. So if you have number of atoms that are there, you produce, it's proportional to that. Then it's proportional to the cross-section that you have, right? And then some sort of efficiency of detection from the detector. This is the material, and this is your instrument. And the way to do this normally, the analysis is done by taking ratios. And if you take ratios, so you have the intensity of element A divided by the intensity of element B. You have a factor which is called KAB, concentration of A and concentration of B. And this factor typically involves the cross-section and the efficiency. And this is instrument dependent. But if you assume that the variation from instrument to instrument is quite small, then you can just measure, you can use some standard values of this based on cross-sections. And we can also show that if you take one element to B and if you have a third element, so if you have IA divided by IC, the two different elements, then you have the same K factor relation between A and C, number of atoms A and number of atoms C. And what you can then do is normalize all of this with respect to one element. And so if you have, so normally what the K factors are done, they're normalized with respect to silicon. So they take Ka with respect to silicon, Kb with respect to silicon. So the ratio of K with respect to A and B, if you don't have silicon, is K with respect to silicon and Kb with respect to silicon. So then you have these numbers that are tabulated, and for a certain material, if you have A and B, you just take the ones that are with respect to silicon, and you get the one that is for the composition that is of interest to you. This assumes no corrections to this. The ZF correction is more complicated. And most of the X-ray machines, when you buy, they will give you a program that corrects for the atomic number, absorption, and fluorescence. But it's a black box, so you have to understand what goes into the black box if you really want to do the analysis properly. Now there are two things that you need to know about this. If you look at that, those figures, that is shown for a scanning electron microscope. So you have a thick sample, you have electrons coming in, and it is expanding in the material, and the X-rays are produced everywhere. Now, in the case of not a scanning microscope, but a transmission microscope, then what you have in a transmission microscope is the situation is slightly different. The different situation is as follows. So in a scanning microscope, you have the electrons coming in, they expand in the material, and you produce X-rays everywhere else. And this is typically of the order of micrometers. It's the order of a few micrometers. Now, if you do a transmission electron microscope, you have to make a very thin foil so the electrons can go through. So if you have a thin foil, you only have a thin section, you only have that part. And if you have only that part, then you don't have to worry about this at all. Because you don't have the absorption, you don't have the atomic number correction, you don't have the fluorescence correction, because it's too thin for it to create any of these problems. So in some way, if you make a thin foil, a very thin foil, and analyze in a TEM, your analysis will be far more accurate than what you would do with an SEM. Is this point clear? Right? The only problem with that is you have to make a thin foil. Whereas here you can just put your bulk sample into the SEM and you can do your analysis. So first you have to make a very thin foil. Second, that thin foil, when you make the thin foil, should not change the material, the composition of the material while you make the thin foil. And the thin foil also has to be representative of your sample. So there are these issues. Once you can overcome that issue of representativeness, if you can overcome that you don't alter the composition while you make the thin foil, then if you can guarantee those two, you will get a much more accurate analysis with the TEM. So this is what you have to weigh when you are in a formal position and you have to find out how to analyze a sample. You have to think through these things. It's easy to stick it in an SEM, but if you stick it in an SEM, you get an analysis, how accurate it is, how important it is for you to get an accurate analysis. Or you're just happy with a ballpark estimate. Right? So those are the kind of issues you need to think through. Okay, any questions at this, up to this point? So we're almost done with X-rays. And we're going to stay, of course, with the atomic structure, and we're going to now go from the atomic structure. What we are going to measure is not the X-rays that come off. We're going to now start measuring the energy of the electrons that come off. The electrons that come off, there are very many different kinds of electrons that come off, and we're going to start looking at this. And in order to do that, we have to understand first how the what the energy levels of the electrons are coming off, but also from a practical point of view, we have to understand how we measure the energy of the electrons that come off. Just like we have these detectors, how are electron detectors built? What is the fundamental underlying principle of the detectors that detect electrons? Okay, so we're going to tackle those 2 points today. So, any questions up to this X-rays? We're going to turn the page and move now to electrons. Okay, so it was a very good question from Sven the last time, and I did not give an exact accurate answer. It turns out that the Auger electrons that come up, so the Auger, let me repeat the process of Auger again. You have an inner shell ionization, just like you have for X-rays. What happens in X-rays is that outer shell electron drops into the inner shell, and the difference in energy between these two levels is given off as a characteristic X-ray. But for that to happen, there are selection rules, and the selection rules determine from which level it can fall to a lower level. And I also told you that this dropping from one higher level to the lower level takes place as a finite oscillation between the two levels. Starts there, it comes down, goes back, and this oscillation has a frequency, and the frequency is given by the energy difference divided by the energy difference divided by h, which is the Planck's constant, gives you the frequency. And then slowly this thing dies down and it transfers from the upper level to the lower level. And for this to create this oscillation back and forth, we have the selection rules. Okay? And that selection rule tells you which specific transitions are allowed. That defines your K alpha line, K beta line, K alpha 1, K alpha 2. We have already explained this 2 classes ago. Everybody's clear on that part. Okay. Now the other alternate process is that you have an inner shell ionization, an outer electron drops in. It does not just produce the X-ray at that point, but the energy difference between those is used to eject an outer electron. So the energy difference then, so when you go from there to here, you have some additional energy. That energy is used to eject an electron. And because of this, because it does not look at just this oscillation, it's after the oscillation is over, and then the energy is given off.
Sorry, so initially a 1s electron is knocked out.
Yes, so
by
the
electron
open
beam.
hole, there's an open here.
Yeah.
and then let us say a 2s electron comes from there to the 1s.
2s go to 1s?
Yes, for the Auger process.
Okay.
It does not, that was the question that Sven asked. It goes for the Auger process, but not for the X-ray process. So the dipole selection rules don't apply for the Auger process. And then that was a very good question. So it doesn't apply, and then that ejects either a 2s electron or one of the other. So there's always three letters to the Auger. The first letter tells you which shell the original vacancy is. The second letter tells you from which shell the electron drops into the original vacancy. And the third letter tells you which electron is then coming out of the sub. So KL1, L1, or you can have L1, M1, M1. Okay, so you have an L shell ionization, an electron from the M shell falls in, another electron from the M shell. And then this is a very special process because it's happening between the same levels. You have an L1, and then an L2, which is the spin orbit split part, comes in, and then the energy is used to do this. This is a kind of a special case. That's where it gets this name called the cost curve. But the basic idea here that you need to know is that 3 atomic levels are involved. You have a level where the ionization takes place, a level from which the electron drops into the originally ionized level, and then the energy difference is used to eject an electron from a different level. So always 3 levels are involved. And you have to, of course, measure that energy of the electron that comes out. And that energy of that electron then tells you about the atomic number of the element that is of interest to you to do the analysis. And so these are, as you can see, the KLL lines, the LMN lines, and the energy lines. You can see the energies of the energies for the various atoms. So these are two competing processes. You have on the one hand the possibility of an X-ray. On the other hand, the possibility of an Auger electron. Yeah.
So if normal selection rules for X-rays don't apply to Auger electrons, do they have their own selection rules? Or further that, why don't they apply by the normal X-ray rules?
Well, that's a little bit complicated physics, you know, so let's just assume they don't apply. And the part of the reason is that when the X-ray transition takes place, for the X-ray to be generated, you have to have this oscillation going back and forth for a finite amount of time. For the Auger, that is not required. You just have to have the energy to drop, and then that energy is used elsewhere. And so from a quantum mechanical point of view, I don't want to go in because I can spend a whole day trying to do the math to explain this to you. But just the basic idea is that the processes are slightly different. Okay. And you can see this energy here, this one, and so on. And so the question is, these are competing processes. And which one takes place is the important thing for you to understand, right? And the key point there is this particular slide. And you can see now how the two things, there are two competing processes. And if you look at the K shell, as you change the atomic number, the Auger for the K shell is high for low atomic number elements. And as you go to high atomic elements, you get the X-ray fluorescence. And it's the same thing with the L shell, Auger, and the L shell fluorescence. So a simple rule that you can take home is that for low atomic number elements, you have a preference for Auger, and for higher atomic number elements, you have a preference for X-ray production. Okay? So that's a rule of thumb. It's not necessarily the case, but you know, there is still, for the very low atomic number elements, you can really clearly see that it prefers the Auger. It produces some X-rays, but it produces more Auger. All right? So this is a very important plot that tells you that here you have the K shell Auger, fluorescence, L shell, and so on. And as you go to higher atomic numbers, the Auger completely drops off and the X-ray fluorescence, so the X-ray production really increases. So the next thing that we want to discuss, which is probably what I will do in this class, and then next class we'll talk about Auger as well as X-ray photoelectron spectroscopy. But all of these depend on our ability to measure the energy of these electrons. So how do we build the detectors to detect the energy of electrons? Okay? The principles are very, very simple. There are only two principles that are used to build these detectors. So one, you apply a constant electric field. If you have a constant electric field, the electrons will experience a force. The force is going to be the charge of the electron, positive or negative charge. We assume there's a positive charge now, and it is going to be. So if you have an electric field in this direction, the electrons will move along that electric field. Actually, it will go opposite because it's a negative charge. But there is electric field. Then there is another very important force, which is when you have not an electric field, but a magnetic field. So when you have a magnetic field, this is velocity times, so if it's going along this direction, this is your velocity, you have a magnetic field going like this. What happened to the electron? So here's V, EV. The B is coming out of the plane of the board. So this is coming out of the plane of the board. So you're going like this, right? EV cross B, but it's negative charge, so it's negative. Okay, the positive charge, it goes, that's for a positive charge. For a negative charge, it's going. So this will move in this direction. Yeah.
In the second equation, what is the symbol next to the B? In the second equation, what's the symbol next to the circle?
This one.
Yeah.
It's a cross product.
Okay.
So I use the circle on top because other people think it's an X, so I just put a circle. So the cross product has a right hand rule. Yeah. Now you can see there are many ways you can do this. Suppose you have a B field like this, or magnetic induction, and you have an electric field like this. Now this is a electric field, and this electron has a negative charge. So what will that electric field do to this electron? Make it go down. So this is the force from the magnetic field, this is the force from the electric field. And now you can balance these two by changing the electric field and the magnetic field, so that electrons of a specific velocity will go, these forces will balance and they will go continuously to go out in a straight line, and you put a small window here, so only electrons of velocity v will come out, and if the velocity is greater than v, some v0 let us say, then if the velocity is greater, you go like this, you'll get blocked, you won't detect it. The velocity is smaller, you go like this, but only one specific velocity will come out. Exactly. So what you'll do is change the B field and the E field, and then when it changes the B field a little bit, this velocity will come out, and then this one will go down. You'll keep changing these to collect intensities of different velocities at any, and so you have a detector here. Now, in this simple design is something that is used all the time. This is called a Wien filter. That's the guy's name, he invented it. So that's it. This is the basic principle of the Wien filter. And as you can see, by just changing the B field and the magnetic field and the electric field, you can bring different electrons to come out here. So that is one way of detecting. This is a little bit complicated one because I wanted to start with it, because the next one is easier, so I can explain it much simpler. So the next kind of detectors that are used, so that is your Wien filter. So there is your Wien filter, and one velocity comes through and you get detected through the hole. The others, higher energy and lower energy, are stuck, they don't come out. And by changing the V and B values, you can just detect energy of the electrons, of the number of electrons of a given velocity. And if you assume that all the electron energy is kinetic, then that you are detecting the kinetic energy. Okay, now the other detector is called an electrostatic detector. So now you only have this electric field, you don't have anything else. So let's just look at A. So what you're doing is you have a region of an electric field, you are sending an electron into that electric field with a certain velocity. So what we'll do, because the electron is now just a positive charge, the electron will move downwards. And because the electron will move downwards, if it has a certain velocity v1, it will, if it has a smaller velocity, it will get pulled down to this bottom surface at a shorter distance. Now, if it has v2, higher velocity, it will travel a little bit further distance before it gets pulled down to the bottom surface. So the V1 and V2, the first two that are shown, shows when the electron enters this detector horizontally. If the electron enters at some angle, that is the one that's shown for V1 on top, then it will come, even though it may have the same velocity as V1 but different from V2, because it's entering at some angle, it could show up at the same point. Now you have to figure out how you're going to collect electrons that are entering this detector at a range of angles, but still come out to the same point depending on the energy itself. So now what you do is you have this kind of entrance. Instead of coming horizontally in, it will come through at a certain angle. And for a given small range of angles, it will always produce the electrons that come out at exactly the same point. And so this is called a linear detector. Okay, and the way it is built here is built in that fashion. So you have these two poles, you have the field around, so that over that small range of angles, you always come to the same value. Then if you want to detect electrons of a slightly different velocity, energy, you change the electric field. You do the same thing. You change the electric field a little bit, so electrons of a different velocity will come back to the same point over the small angle. So it's called a linear detector. You detect one at a time. This one is a cylindrical detector. So there are two pole pieces, but assume this is a whole cylinder. And you go here and you go in there, and the both of them over that whole range of angles will converge to the same point. This is called a cylindrical. It's just the way the electric fields are designed. So you have one concentric cylinder inside and another cylinder outside with the potentials. So electrons are coming in at a certain angle, they get reflected. You change the potential here to detect them. These are commonly used in X-ray photoelectron spectroscopy.
So you're only getting a specific angle, but you're getting many velocities?
You get a single velocity over a range of angles. So over a finite small range, or even though they don't enter at the same point, if they enter at a small range of angle, they'll still come back to the same point. And then you change the field to get a different velocity come to the same point. So this is purely using the electrostatic field. The advantage of this is that it's very simple, small, compact, and you don't need any kind of coils and wires to build the magnetic field. So it can be built in a high vacuum environment. You don't have other things that will contaminate the high vacuum environment. So this is for using the electrostatic field, and then you can just use the magnetic field. And if you just use the magnetic field, you can also get the same dispersion, as they call it. So you have electrons of a certain velocity coming in, you have the magnetic field, the region of uniform magnetic field, you have the Lorentz force, and when the Lorentz force is applied to the traveling electron, it creates a force perpendicular to the direction of motion, and that is similar to a centripetal force. Eventually, as a result, the velocity, a linear trajectory, becomes a circular trajectory with a finite radius determined by the magnetic field. And then, as a result, will come, and the radius will change depending on the velocity that you have. And therefore, the velocity of 1 will come here, velocity 2 will come out at that point. Now you can either have an open slit that you can detect one velocity at a time, or you can have a position-sensitive detector that detects the intensity at different positions, and then you can have the whole spectrum displayed at one time. So if you go and see certain electron microscopes that have at the bottom an energy loss spectrometer, they're often, not often, they're almost always designed using a magnetic sector and a position-sensitive detector. So this is how you measure the energy of the electrons. So there are 3 ways you can do it. You can use an electric field, or you can use a magnetic field, and if you want really fine sensitivity, then you can use a combination of these that will give you much finer control and an energy resolution in these detectors. So that's all you need to know in terms of how electrons are detected, or energies of electrons are detected. Huh? Go ahead, ask a question. Yes, because you're assuming all the energy of the electron is kinetic. Because if it has a potential energy component and you're only measuring velocities. So you're assuming now the energy is all kinetic, half mv squared. So can the same detectors be used for detecting other things other than electrons? Any charged particle. So if you're going to use helium ions or protons, so you can use alpha particles, which are helium ions, you can use protons, and you can use the same detector philosophy to detect that. So later when we talk about ions, how we use ion-based scattering methods or ion-based spectroscopy methods, we will use the same detectors. The only difference here is that here the charge is negative, and for the ions, the charge is positive. And therefore, you have to be careful about how you do the balancing. And the same thing, you have to also, when you use the filters I showed you, the electron, the charge is positive rather than negative charge. But essential physics is all the same. The only difference again is that the mass, if this is the mass of an electron, and that if you use a proton, it's the mass of a proton. One of the things you should really remember is that the mass of the proton, is it the same as the electron? What factor is it higher? 3 orders of magnitude. It's 1,000 times, a little bit over 1,500 times the mass. So everything, the big difference is the mass. Okay? As long as you remember that, and then the other thing that we will talk about at some point is neutrons. They also have mass, but they don't have charge. So when they scatter in solids, when they have low charge, they have less scattering. And that means they penetrate larger depths, neutrons. And therefore you need thicker samples to get anything for the neutrons to interact with your material. So typically when you do neutron experiments, you need thicker samples. So we make very, very thin films, you can't really use neutrons to study them because they don't just interact at all. Right? So you have to remember these very basic ideas when we look at different characterizations. So in the next class, we have a few minutes. I want to set you up for the next class. So the technique we are going to discuss in the next class, we're going to discuss both Auger, how we detect Auger electrons, and also how we detect what are called photoelectrons. So the photoelectrons are very simple. So you have an X-ray photon coming in. It hits one of the electrons of the solid, typically a core electron. It transfers all its energy to the core electron, and the core electron then comes out of the solid. And when the core electron comes out of the solid, it has an energy. Is its energy the same as the initial photon or not? What is it? Shaking your head.
Oh,
Yep.
I don't know.
You should know. It is the photon minus something. What is that minus something? Well, work function, before the work function, there is something else. So, binding energy. So you have this electron that is bound by that certain energy. This X-ray photon is coming, has to knock it off. And therefore, when it knocks off, if this electron has 1,000, X-ray photon is 1,000 EV, if this is bound by 100 EV, then it's going to come out with 900 EV energy. Then there is a small little bit of the work function because it needs to have a little bit of energy to come out. But in the larger scheme of things, for the moment, we can ignore the work function. Right? So you have 900 EV coming out. Now, that's the first one that says EC. Okay? What it also can do is, as the electron is coming out, it can hit something else and lose a certain amount of energy. And that means that is the delta E, is the energy loss. And then if it's coming out from very deep in the crystal, then it gets scattered and the crystal never comes out. Now for your X-ray photoelectron spectroscopy, you really want to detect EC, which is the energy, which is the initial energy minus the binding energy. So you want to see only the surface. The electrons coming out from the surface, because anything that's coming out a little bit deeper is lost some energy due to the so-called inelastic scattering. So this technique is really, really good at analyzing the surface. So this photoelectron spectroscopy is really a surface science technique used to analyze a surface. And the reason it is used as a surface technique is because of this. It's a very important plot. Here, what is the mean free path length? How much distance the electron travels before it hits some other object and loses some energy. And this shows the electromagnetic energy in the solid. And over all the way up to 2 keV, for all the elements, the maximum distance it can travel is 1,000 angstroms. For most, 100 angstroms. And for most of the elements, it travels between 5 and 10 angstroms before it hits some other electron, and loses energy. This is why this is surface. We'll take it from here in the next one.